All right, so this is Unit 3, and we're going to be talking about the periodic table. Now, this is a very important unit in that the information that you're going to gather from this is going to carry on for all of the rest of Chemistry A and certainly be required in Chemistry B. So, since we're talking about the periodic table, I'm going to start from the very beginning of it. You have a guy from Russia, Mendeleev, who is really given credit for organizing the known elements of the time into what we know as the modern periodic table today. But a lot of the time we skip over another guy, Lothar Meyer, who is from Germany, and they both created their own organization of the elements. So they created their own periodic table. But the problem is, Mendeleev got his published quicker, that is, his publishing company got it out quicker. You know, back in those days, they published books, not just charts. And so Mendeleev's company got it published before Meyer's, got his out to the public, and as a result, Mendeleev got the credit for the periodic table, although, well, to be honest with you, somebody else did the exact same work, but that's just how it works in science. And so here is a picture of that print. However, I do have a picture of his handwritten periodic table coming up, which is really cool. Now, we've talked about the periodic table a little bit in class so far, and you know that it is organized in groups and it is organized in periods. And so you can see he's got groups on the top, periods on the bottom, and you can see the different elements. And you know, you can see some of the pattern that's still holding today, but it is obviously, well, it's been improved over time, and other elements have been discovered since then. And that's one thing, Mendeleev actually was able to predict elements on the periodic table that he felt like future scientists would discover based off of his organization on periodic trends. And so Mendeleev organized his table in such a way that he was able to say, you know, I really think there's probably an element in between, element A and element C. And sure enough, that element B was discovered. And that happened quite a few times from 1869 to the present time. And this also didn't hurt in his recognition for the periodic table. So here's a picture, by the way, of Mendeleev's original handwritten table. This is pretty interesting. And again, this is what was published in 1869. Now, as you can see, he arranged his table vertically by mass rather than horizontally as we do today. But that's not really a big deal. I think it's just cool that you see the original periodic table. And in class, I'll show you a video or two with regard to it, but here we are not going to do that. All right, so you know, you saw the original periodic table developed by Mendeleev, and now you can see what it's morphed into today. But when you see this table, Mendeleev is the guy who you need to give credit to. And don't forget Lothar Meyer also. So we've got 8 groups, and let me show you what a group is. And that's labeled here on this table for you. So you've got group 1, you can follow my mouse. You've got group 2. Now these here in the center and on the bottom are called transition metals. So we're going to pretend they don't exist for a little while. Here's group 3, as you can see. Group 4, group 5, 6, 7, and 8. Some periodic tables will call this group 13, 14, 15, 16, 17, and 18 because they go ahead and give these a specific group number also. Other periodic tables don't. I prefer this way. It's much more simple because you're going to find that the transition metals have their own unique properties, and we'll talk about that in a little bit. So for all practical purposes, there are 8 groups, and you read them from top to bottom. 1, 2, skip these in the center, and then you go 3, 4, 5, 6, 7, and 8. And there are 7 periods. So you read the periods going the other way. So a period is here. You've got period 1. You've got period 2. You've got period 3. So we're going left to right now. period 4, period 5, period 6, and period 7. Now let me be clear. The lanthanides, we call these here, and the actinides on the bottom are all part of the transition metals. These bottom two rows are supposed to be in the center here, but to keep the periodic table clean and organized, we broke really what should go right here in red down to their own specific periods on the bottom. But be aware, the lanthanides 57 through 71 technically go right here in group 6. The actinides 89 through 103 technically go here in the last period 7. All right, if I said group right here, I meant to say period for the lanthanides, but you get the idea. This is color coded. You've got your metals in this tannish color. You can see most of the periodic table is a metal. You've got your metalloids here. This is called the stair step normally because it forms a stair step like pattern. You can call them metalloids or semimetals, and then you've got your nonmetals here in green. So the modern periodic table is organized by groups which go vertically and periods which go horizontal. So you've got your groups, there are 8 of them, and your periods, there are 7 of them. But there's some extra information that is carried by the group number specifically. So as you can see, the group number represents the number of outermost electrons. The outermost electrons are called valence electrons. So if you're in group 1, you have 1 valence electron, 1 outer electron. If you're in group 2, you have 2 valence electrons or outer electrons. Group 3, you have 3, 4, 5, 6, 7, and 8 outermost, or we call them valence electrons. And we're skipping the transition metals here. With the periods, the period determines the number of shells. So think of shells as circles. You've got the 1 shell, 2 shells, 3 shells, 4 shells, 5 shells, 6 shells. Remember, technically this goes here, and then 7 shells, and the pink goes here with the pink. All right. Let me show you pictorially here. So here's your atom. You've got the nucleus, which contains your protons and your neutrons. And this gold shell here has some electrons, but it's not the outermost electrons. Likewise, this green shell here has electrons, but they're not outermost electrons. We call these core electrons if they're not the outside band. In blue here, though, you do have the valence electrons, the outermost electrons, because they are the furthest away from the nucleus here. So again, the group number determines the number of valence electrons. Let's count. We've got 1, 2, 3, 4, 5, 6, 7. We've got 8 valence electrons. So we would know then that this is an atom within group 8 on the periodic table. So again, I've got this spelled out for you. I know it seems redundant and a little bit silly, but this is critical, and you will certainly be given a pretty massive quiz over this. All right, so the group number, you read groups top to bottom. There are 8 of them, and the group number corresponds to the number of the outermost or valence electrons in the atom. This comes in really handy with chemical bonding, which we'll be covering in Unit 5, I do believe. Actually, chemical bonding is in Unit 6, but Unit 5 is periodic trends, and we'll revisit this idea then also. So again, here's your periodic table. I'm going to go back to this slide quite often, but here's what you want to gather from this new one. 8 valence electrons gives an octet. Atoms are stable only when they have 8 valence electrons, or 8 outermost electrons. That's why chemical bonding, which we're going to cover in a few units, exists. If the atom does not have 8 valence electrons, it's going to do everything it can to get them, and that's usually chemical bonding. So 8 is the magic number. For example, oxygen has, well, 6 valence electrons. So does selenium because they're in group 6. They want 2 more valence electrons to get 8. Beryllium has 2 valence electrons. Likewise does barium and radium and all of the other group 2 elements, right? And they want 8 valence electrons likewise. We'll talk about how they get them in a later unit. But no, 8 is the magic number. And I'll go ahead and say this to prepare you for later. Don't worry about all these electron configurations. This is coming up next in Unit 4. But here's the deal. Group 1 has 1 valence electron, right? As you can see here. Group 1 has 1 valence electron. How do they get 8? Well, you can gain 1, 2, 3, 4, 5, 6, 7 more, which could be done. But you know what? It would be a whole lot easier for lithium to lose its 1 valence electron to get to 8, right? And so group 1 is going to lose 1 valence electron. And when that happens, for example, when lithium loses its 1 valence electron, it's going to be like helium that has 8 valence electrons, right? So the group 1 metals are going to lose 1 valence electron, forming a +1 charge. Now this throws people off left and right, but think about it. Electrons have a negative charge. If you lose something that's negative, you're going to become that much more positive. So since you've lost 1 negatively charged electron here in group 1, you got a 1 positive charge. The same really for group 2. Group 2 metals can either gain 1, 2, 3, 4, 5, 6 valence electrons to get 8, or they could just lose 1, 2 valence electrons to get 8. So for example, beryllium here, if it lost 2 valence electrons, 1, 2, it would become, again, like helium, which already has 8. It's easier to lose 2 than to gain 6. You just have to think about it in that way, and that rule always holds. So in order to achieve a full octet, if group 2 loses 2 negatively charged electrons, their resulting charge is going to be 2 times more positive because they've lost those 2 negative particles. Remember, we skip all of these here in the center. Group 3 metals has 2 choices. They can gain 1, 2, 3, 4, 5 valence electrons, or they can lose 1, 2, 3 valence electrons. So it's easier to lose 3 than to gain 5. So for example, aluminum here, it can lose 1 valence electron. It would be like magnesium. It would lose 2 valence electrons and look like sodium, or it could lose, and then when it loses its 3rd valence electron, it looks like neon, which is a noble gas with 8 valence electrons. So if you lose 3 negatively charged particles, you're going to have a positive 3 charge. Group 4, on the other hand, is special. Because think about it, it can either lose 1, 2, 3, 4 valence electrons, or it can gain 1, 2, 3, 4. So group 4 is actually not going to form a charge. And we're going to talk about that more when we study chemical bonding. Now let's look at the non-metal side of this. And these, to me, are easier. So for example, you've got group 7 here. Group 7 only needs 1 more valence electron to become like group 8, the stable ones, right? And so here's the deal. If you gain 1 negatively charged electron, then you're going to have a extra -1 charge. Let's look at group 6 here. Well, they need to gain 2 electrons, right? So if you gain 2 negatively charged electrons, you're going to have a -2 charge overall. Group 5 here needs 3 negatively charged electrons, so it's going to form a -3 charge. So again, for these, it's easier to gain valence electrons to get 8 then to lose, right? So it's just you have to think about which one's which. So group 1, group 2, and group 3 will always lose valence electrons. As a result, they'll form a cation, which always has a positive charge. Group 5, 6, and 7 will gain valence electrons, forming an anion, and they'll always have a negative charge there. So if you remember, looking back, we said that the number of periods represented the number of electron shells. Let's revisit that, okay? So here is a shell right here. This is the nucleus. Here is your first shell. This is period 1 on the periodic table. So that corresponds to period 1 right here. So this has 1 shell. Now you can think about what it looks like. Now let's go to period 2, which has 2 shells. So period 2 on the periodic table has these 2 rings, or these 2 shells, which is right here, right? So all of these atoms just have 2 shells, or 2 rings, when you draw that atom. Here's period 3, period 4, period 5, period 6, period 7. So here's period 1, period 2, period 3, period 4, period 5. And then if we had a 6th period, we'd have a 6th shell. And if we represent the 7th period, we have a 7th shell, right? So every time you go down a period on the periodic table, you gain an extra shell or an extra ring when you're drawing the model of the atom. And remember, that's just where you can place electrons. So there's your idea of the shells. And so now you've really got a large majority of the periodic table already learned just by going through this portion of the video. Now let me give you some general properties of the metals, nonmetals, and the metalloids. All right. So this is just to give you an idea of where they're all located. Most of the periodic table is metals, although hydrogen exists predominantly in a metal category, but realize technically it should go, or it could go right here, but for technical reasons it doesn't, and hydrogen's a non-metal gas, obviously. So let's start with the metals here, the blue, all right? So first things first, where are the metals located? Now, I'm not talking about transition metals. Yes, they're a metal just like all of these I'm fixing to discuss, but they're going to go in a category of their own. So remember, the transition metals are here on in the blue, right, including the lanthanides and the actinides on the bottom. But we're going to talk about group 1, group 2, and group 3 metals first. So the metals that are not transition metals are located in group 1. Now remember, hydrogen technically isn't a metal. And group 2, and also in group 3 right here. I know this is a metalloid, but work with me here. Group 1 is called the alkali metals. And group 2 is called the alkaline earth metals. These metals, as you can guess, are very existent in our Earth's soil and the Earth's crust likewise. The alkali metals are also abundant in the Earth. The difference is these are very, very reactive. Group 2 metals are reactive also, but they're not near as reactive as the group 1 alkali metals, all right? But they're both extremely reactive. Group 3, as I've shown you, is also a part of the regular metals, group 1, 2, and 3. They're not very reactive. Think about it. Group 3, you've got aluminum, for example. Well, we make aluminum foil, right? So it's obviously not incredibly reactive. So those are the main group metals, group 1, group 2, and group 3. But hey, realize one more time that hydrogen technically isn't a metal, and neither is boron in group 3, all right? But we're not going to be that nitpicky here, all right? So here are some general properties of metals. And likewise, these basic properties correspond also to the transition metals, but we're going to go into more detail with those in a minute. So common examples are copper, lead, silver, and gold, right, like coinage metals. All metals are malleable, except for mercury. Mercury is the only liquid metal. All right, so every metal except mercury on the periodic table fits this description. So for a metal to be malleable, they're easily bent, easily shaped, right? Which makes sense because we use them for buildings. They're ductile, so you can easily draw them into wires. Think about copper wiring. They're good conductors of heat and electricity. And on the molecular level, all this is possible because of something called sea of electrons. Essentially, the electrons group together in a metal, and when you add electric current, since the electrons are all grouped together, they can just flow through those electrons, or that sea of electrons, relatively easy. You'll learn about this probably about the last week or the next to last week in Chemistry A. So I just want you to be familiar with it ahead of time. And this is why they have a shine associated with them. All right, so I gave you all of the properties of the metals, right? So every one of these are metals, but we've only specifically talked about the properties of group 1, 2, and 3. So let's talk about the transition metals, all right? Transition metals, along with the properties I just told you about a second ago, also have some different properties too. They have the usual properties of the metals. So transition metals have all of this. This is applicable. But they also have some other odd properties. They're called heavy metals because they have a large number of protons and neutrons. Think about it. Some of these metals here have like atomic numbers of 100 or even, or more common like 80 or 90. That's a pretty heavy metal, and because they have so many particles on them, that gives them kind of odd properties. To be honest with you, it makes a lot of them radioactive, which we're going to talk about, and which we really already have talked about to some extent. So they have great variance in chemical reactivity. This is due to having a large number of protons and electrons, and you will see that in a greater extent in the next unit when we talk about their electron configurations. They have some pretty odd properties there. As you learn from Unit 2, they're radioactive, right? And so the heavier the element, the more particles it has, the more unstable the nucleus tends to be, and then that is what leads to your fission and also fusion, but fusion is a little bit different because it deals with smaller particles combining. But radioactive elements give off very harmful radiation, like gamma rays, which we talked about in Unit 2. We're going to talk about in greater detail in Unit 4. They're coinage metals. We talked about that. They're often considered a separate group on the periodic table. I think you can see I have treated them that way due to these varying properties. So we've got the metals covered, right? Group 1, Group 2, and Group 3 are just kind of your regular metals. And then you can add the transition metals in a separate category there. But they're all metals. They just have different properties. All right, so next let's talk about the nonmetals. You see the nonmetals are located to the far right of the periodic table. These are the ones that instead of giving up electrons to form a positive charge, they gain electrons to get that full octet, and they form the negative charge. So some basic properties of nonmetals: they mostly exist in the solid or gaseous form. Bromine is an example. Bromine is an exception. So bromine is the only liquid nonmetal. And think about it, mercury is an exception to metals because it's the only liquid metal. All right, so most metals are solids or gases. Bromine's a liquid, as you can see here. This is a liquid, but it's volatile, so it does produce toxic fumes. All organic compounds. So organic compounds usually contains carbon. We've already talked about that, right? Like our biological makeup. So, also phosphorus, nitrogen, so on and so forth are nonmetals. Common examples: chlorine, carbon, oxygen, xenon, but really anything on the far right of the periodic table, as I've already told you. So metals, in contrast to nonmetals, they're not ductile or malleable. You never hear about oxygen wiring. I mean, first off, that's not even a solid. So they do not conduct heat and electricity. Minerals in drinking water. So later on, we're going to learn about these polyatomic ions, namely phosphates, carbonates, sulfates, so on and so forth. They're all non-metals, but they are found in drinking water, right? So it's pretty common. It's pretty important. That's what gives water kind of a taste, are the minerals in there. By the way, the only time you ever drink pure water is when you drink distilled water. So the distilled water has all of these minerals evaporated out of them, essentially. But if you drink spring water or whatever else, they've got minerals by definition, or well water. Nonmetals easily react with other elements. Now, they don't react with noble gases. And think about why. What did we just say noble gases were? Well, they're stable because they have 8 valence electrons. So the only thing that a nonmetal won't react with is something that already has a full octet, 8 valence electrons. These are called the noble gases. No reactions occur with them because, they're already stable, so there's no point. Our atmosphere consists of pretty much all nonmetals. People think that oxygen is the most abundant element. But what people don't realize, there are these things called oxidation reactions. If the air was mostly oxygen, we would burn up alive, which we don't want to do. 80% of the atmosphere is nitrogen. So every time you take a breath, you're inhaling 80% nitrogen and 20% oxygen, roughly. There are also some trace elements in there, but the atmosphere doesn't have as high of oxygen content as you would think. So here's an application. Back about 5 or 10 years ago, there was this push for putting nitrogen in your tires. They said it increased fuel economy. Well, so they put the little green caps on the valve stems to represent their nitrogen field. And people, when their tires got low and they had to air them up, they were like, well, goodness, if I add oxygen to the tires, it's going to mix with the nitrogen and they're going to blow up. And that's just really ignorant because 80% of the air is nitrogen anyway. So, if you have a compressor at your house where you can just air your tire up on your own, that compressor sucks up air from the atmosphere. And so you're getting 80% nitrogen in your tires anyway. So it's a gimmick. So the halogens are an important non-metal group. They're group 7 on the periodic table. So let me go back really quickly. I got to go through quite a few slides here. But group 7 is right here. These are your halogens on the periodic table. They have 7 valence electrons, and they are salt formers. So the word halogen means salt former. That means they easily react with alkali metals, which is group 1, or alkaline earth metals, which is group 2. So the word salt, people think is table salt, right? Sodium chloride, and they're right. But by definition, actually a salt in chemistry is any group 1 or group 2 metal bonded chemically to a group 7 nonmetal, and that particular group is called the halogen, just FYI. Fluorine is the most reactive halogen, but the entire group is extremely reactive. And why? Well, if you're in group 7, which is the halogens, then you need 1 more valence electron to get an octet, to get 8, right? And so they're just 1 away, so they're going to do whatever they can to get that 1 electron to be stable. That's why they're extremely reactive. So when the halogens or the group 7 nonmetals do gain that 1 valence electron to get a full octet, they form a noble gas. So the noble gases is the nickname for the group 8 metals on the periodic table. They have 8 valence electrons. That means they have a full octet, meaning they're stable. So I'm going to digress for a second. Group 1 has 1 valence electron. They're going to lose a valence electron to get an octet to become like a noble gas. Group 1, though, is called the alkali metals. Group 2 is the alkaline earth metals, and they will lose 2 valence electrons, forming a positive 2 charge to become like the stable noble gases, right? So alkali metals, alkaline earth metals, halogens, and the noble gases. Those are some of the slang names that I expect you to gather. So because they're so stable, they don't react with other elements. That means they're an inert gas. And since they're a gas, you can use them in signs. You can put a little bit of electricity in there to excite them. We'll talk about why that produces a color in the next unit. It's not that they conduct electricity, it's just that you're exciting electrons. And we'll talk about that later. So since they're stable gases, they can be used in signs, and they produce neat colors also. So that's another benefit. We talked about metals. We've talked about non-metals. Let's talk about the metalloids here, which form this stair step on the right side of the periodic table. Now, you can also call them semi-metals. Some scientists would go on a rage about that, but I absolutely could not care less. The metalloids are probably what you're most interested in, because in your pocket right now, I guarantee you have a device that contains a lot of these semi-metals. So they're boron, silicon, germanium, arsenic, antimony, beryllium, and polonium, as you can see again, as I have listed for you here. By the way, antimony is not AT, it is SB. They're in between, meaning they have properties that are in between that of metals and non-metals. So for example, metals conduct heat and electricity, non-metals don't. These are in between, so we'll call them decent conductors of heat and electricity. And as a result, we call these semiconductors. So why are these so important in technology? Well, let's think about it. So say that you have a circuit board in your computer, which obviously you do. So think about the processor, more than likely Intel, it could be AMD, processor in your computer right now. If you had a straight up metal wire leading from the battery to the processor, well, those conduct electricity almost too well, and you would burn up the chip or the circuit board. You probably don't want to do that, right? So, okay, well, you don't want to have too much property that can fry your circuit board, or too much electricity that can fry your circuit board. So, let's use a non-metal. Well, they don't conduct electricity at all, so they never get power, so they never power on. So those metalloids or semi-metals have in-between conductive properties that are, quote-unquote, just right. And so these are just some of the applications that they're used in. There are many, many more. LED light bulbs, though, think about that. LED bulbs are kind of a recent thing. So we're going from these old incandescent bulbs that are wildly inefficient. We'll talk about that in Chemistry B. And we're moving over from those old-fashioned filaments that produce more heat than they do light over to these LED bulbs, which are very cost-efficient, and they're made from these semi-metals. So conductance falls somewhere that between a non-metal, which is an insulator, right, and a strong conductor, which would be a metal. All right, and so here's the deal. Silicone is a semi-metal or a metalloid, right? Here's silicone. Silicone is one of those metalloids that's widely used in computers and in technology, and so that's why in California, all of the or a lot of the big tech companies are located in what is called Silicon Valley. All right. And so a lot of students have asked me, why are some of the names on the periodic table different? For example, iron. Its chemical symbol is Fe, and that actually comes from a Latin name, ferrum. And there are a bunch of other examples like that on the periodic table, and perhaps you've identified some already, and we've talked about that in class. But I want to show you where a lot of these names for the elements came from. But first, just remember you have all of these squares for each of the 118 elements on the periodic table. This is exactly how it's printed on every periodic table. The number on the very top is the atomic number, which you should remember from Unit 2 is the number of protons, which is the same number of electrons. You have the chemical symbol here. You have the name represented by the chemical symbol and the atomic mass. And I've already went through the whole spiel on the atomic mass, that it is an average of all the isotopes for each element, right? But you use this in AMUs, but more commonly grams. So that's just kind of a review. What's an elemental name? So I've got, I think, 3 or 4 slides of this. And, for example, iron, its chemical symbol is Fe, and it has an Anglo-Saxon origin to it. Also, though, it's got some Latin behind it also. Iron, actually, what we call it today is Anglo-Saxon, but ferrum, the Fe on the periodic table, is Latin. So anyway, this is the elements to some of the origins to some of the elements. Look at these. So the origin behind some of the names here on table A2 are with regard to colors, which is really, really cool to think about. So rubidium, Latin, like a ruby, right? It means deep red. And then we have just a lot of these named after people. So we've got an element named after Ernest Rutherford, who discovered the proton. There are also elements named after countries or even states. In fact, there's an element on the periodic table named after the state of Tennessee. All right, here's the element from America. Is the Tennesseum on here? I don't think it is. But anyway, you got Californium because it was discovered in California, so on and so forth. These come after usually Greek gods. As you can see here, some of these names or planets in the solar system, but you have to remember at the time, years and years and years ago, these were considered heavenly bodies. And then you've got more. So I encourage you to look at this. It's pretty cool. But there is your outlook or your overview on the periodic table. Just remember, this is not meant in any way to replace class. So just remember that, and have a great day.